Okay, we are looking at pH and pOH of strong acids and bases. Key idea is strong. Strong is simpler. Weak, ugh, not so easy. So dissociation of strong acids is then coming apart in water. Strong acids are assumed, again, in reality there is some differences, but we're going to assume that they dissociate completely in solution. So whatever we have here, we get the full amount in proton and conjugate base. Now, large Ka or small, very large. All products, very little reactants. Ka is products over reactants, therefore it's going to be very large. Just like we said, product favored, much more product. That's what makes these far simpler. Examples of these strong acids, and you should know these strong acids. All of these here, take off the hydrogen, you get the conjugate base. The Ka is very large. I don't even know if I've ever seen what those Kas are because they're just enormous, right? I looked at this one and go, why is that 1? Well, if you've got this reacting with this, guess what? You get H3O plus and H2O. So essentially your concentration does not change before and after, so it's 1. So what this means is that because your Kas are very large, whatever your concentration of your strong acid is, 0.125, 0.054, whatever those values are, that is the concentration of your proton, of your H+. So then calculate pH. Again, your pOH is 14 minus that. And again, keep in mind, these are acids. If these were bases, which we'll get to, something a little different. Now there's di- and triprotic acids when they have multiple hydrogens to lose. When you look at some of these here, these are the first acids or hydrogens to be lost. Sulfuric acid, strong acid, it's very high. Then you can see there's a pretty big drop off for these di- and triprotic acids because, again, they're not very strong, or they're not strong at all. They're weak acids. Now, even in this first one, these are kind of in the reasonable range as far as our Kas. Then they get pretty large to where it's going to be unlikely that even one of these is lost to a large amount. Ka for the second hydrogen is always going to be higher. And you can see it's an order of magnitude of, 100, 1,000. What is that? 100,000 times 5. This one's for some reason pretty short, citric acid, not sure why. But you can see the second order of magnitude is huge. So no matter what these concentrations are, you're going to be adding something, to the thousandth, 10,000th, 100,000th. It's going to be insignificant. So after the first one, what remains is a weak acid. It have its own thing, but it's so minuscule, you're only really going to be worried about that first part. Strong bases, similar but different, and that's because they do something different in solution. So these are group 1 and group 2 hydroxides. All of them found here. The idea is that when you have things like aluminum hydroxide or copper hydroxide, most of those are insoluble. So therefore, their Kb would be a weak base, not a strong base, because they don't dissociate very strongly. So because these are ionic solids and they're strong bases, meaning they essentially 100% dissociate. Group 2, you have to be careful though, because there's 2 hydroxides. So the concentration idea is that once they break up, it's twice as basic as it was before. Okay, I should say as a group 1 hydroxide, because it's producing twice as much hydroxide as a part of that. So if they ask the original concentration, it would be 1/2 the original. So what I mean that if it gives you hydroxide concentration is 2 molar, that means the original concentration had to have been 1 molar. However, this is also 1 molar. So it's very simple to get either lost, confused, tricked, as some people might call it, into thinking it's a different amount based upon the separation. And this is not true with acids. H2SO4, that first acid, boop, it's gone. The second one, it's a weak acid, and so it's most likely retained. But this is in full, so be careful of your concentrations. Remember, this gives you hydroxide, so if you do the P of something, you're going to get the pOH, which again, 14 minus the pOH equals your pH, and you should be good to go for pH. Because pH is what it's the pH scale, not the pOH scale. However, keep in mind that you're going to be dealing with bases and hydroxides quite a bit. So now we start getting into the reason why this unit is quite tricky. So you want to be able to determine these based upon the concentration of all species in a strong acid or base. And what I mean by all species is that, let's say they give you the concentration of the acid, strong acid, or concentration of the strong base, or give you the concentration of hydronium in a base, or give you the concentration of hydroxide in an acid, or give you the concentration of the group 2, the group 2 positive ion in a base, or give you the conjugate bases concentration, and you need to determine these. So you have to be able to go from one thing to another using those concentrations. Now, they all use the same math, but just be aware of what they mean in reference to each other. If there's a mixture of strong acid or strong bases, so let's say you have potassium hydroxide, KOH, and lithium hydroxide, those come with their own concentrations, correct? Let's say both 0.1. However, the concentration of hydroxide, both being group 1, would be equal to each of theirs of 0.1. However, you're putting them together, so it would be 0.2. So those types of things, needing to total up all the hydronium, or I should say proton, H+, and OH- to get the proper amount. We're not talking acids and bases mixed together. Those are reaction titrations much later. Much more math. You also want to focus or have the focus or knowledge of the problem that it may have other ions concentration that you need to infer. Much like if I give my example down here, they may give you information here about the barium ion, but you need to infer what this is and maybe what pH and pOH is that. So they most commonly want pH, but of course there's always going to be questions about what is the pOH of this. Another thing that's come up across this whole unit is be careful of volumes. So, for example, in my previous talk up here, I talked about lithium hydroxide, potassium hydroxide, right? Both being 0.1 molar, we would say that the hydroxide concentration would be those added together. However, you have to be cautious how much of each you're adding, because different volumes are going to produce different concentrations. So when you add the two concentrations together, I should say the two volumes together, you get a new volume. And remember, concentrations are always moles divided by the volume, often in liters. Right? That's what we're talking about, molarity. That's what this is referring to. So be cautious that if you're adding solutions together, whether they be two acids together, two bases, or of course, when you add an acid and a base together, you're going to get a different volume, that the concentrations will change just due to the volume change. That comes up quite a bit, so keep your eyes out for those. That's a good thing to highlight when you have two volumes added together. See if that's going to have an impact to your problem. All right, coming with all your kind of stuff. Next, we got something a little more complicated.